Welcome viewers, in this video we'll see the resonance in a parallel practical circuit. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Now we'll go to the topic practical parallel circuit. In that we are going to verify the resonance. Let us consider the parallel circuit. There are two branches available. In the first branch, resistor and inductor is connected in series, that is parallel with the capacitor. Capacitor is connected individually. R and L connected in series in parallel with the capacitor. So this is the applied voltage E. Current I is available. Due to parallel, the current is divided. The current through this RL is IL. Current through the capacitor is IC. The total admittance of the circuit Y equal to YC plus YL. This admittance is nothing but reciprocal of the impedance. So the YC can be written as 1 divided by ZC. Similarly 1 divided by ZL. ZC is nothing but capacitor is minus JXC. ZL resistor and inductor is connected. So R plus JXL. Right. So this is the total admittance. Now we'll go for the further simplification. In order to bring the term this J available in the denominator, in order to bring in the numerator, it is multiplied and divided by the J, complex conjugate. This term is multiplied and divided by R minus JXL divided by R minus JXL. Here R plus is there, so it is multiplied by R minus. So the J is available here. Here J square. J available 2 times J square. Minus is also there. So J divided by J square XC. This term is JR minus JXL divided by, so this is nothing but A plus B into A minus B. So that is A square minus B square. A is R square. B is JXL, J square XL square. We know that J square value is minus 1. Here also J square is minus 1. Here minus available, minus into minus become plus. Here also minus into minus become plus. It become the plus, the symbol become plus. So J divided by XC plus R minus JXL divided by R square plus XL square. Right. Now this term is splitted. R divided by R square plus XL square minus JXL divided by R square plus XL square. Now we'll combine the real terms and imaginary term. This is the real term. R divided by R square plus XL square plus we'll take the J commonly in the imaginary term. So we'll take 1 by XC minus XL divided by R square plus L square. We'll take this equation number 1. So now it is available in a complex form. Real term and imaginary term. That is a reactive part. Real part and reactive part. So at the resonant condition, the reactive part is 0. The resonant condition, the reactive part of admittance is 0. This term is 0. That is the condition for resonance. 1 divided by XC minus XL divided by R square plus XL square equal to 0. Bring this term that side, so the negative become positive. Right. Now cross multiply the terms. This term is multiplied here. Now we'll cross multiply these terms, so that R square plus XL square equal to XC into XL. We know that XL is omega naught into L. XC is 1 divided by omega naught C. This omega naught got cancelled. So it becomes L by C. Now we'll go for the further simplification. So R square plus L square XL square equal to L by C. Now bring this term R square that side, so that XL square equal to L by C minus R square. Take square root on both the sides, so that XL equal to square root of L by C minus R square. This XL is nothing but omega naught L. Right. Bring this L in the denominator. So omega naught equal to 1 by L square root of LC minus R square. Now we'll go for the further simplification. Now this bring this 1 by L inside. So it become 1 by L square. So L divided by C into L square. R square by L square. This 1 divided by L goes inside, mean it become L square. So 1 L got cancelled here. So 1 divided by LC minus R square by L square. So this is the resonant frequency in the radian per second. In cycle per second, f naught equal to omega naught divided by 2 pi. So this f naught equal to omega naught available here. So 1 divided by 2 pi square root of L1 divided by LC minus R square by L square. This is equation number 3 and equation number 4. Now we'll go for the further analysis. At resonance, the admittance is denoted by Y naught. Y naught equal to R divided by R square plus XL square. Z naught is the impedance at the resonance. That is nothing but 1 divided by Y naught. So from equation 1, we are writing this. At resonance, this Y naught is written from the equation 1. So 1 by Y naught mean R square plus XL square divided by R. Y naught is, this mean 1 divided by Y naught, this value. Right. But this R square plus XL square equal to 1 by C from the equation number 2. So this term is replaced by L by C. So C will go on the denominator. So L divided by CR. The impedance at the resonance Z naught equal to L by CR. Now we'll see the further details. Z naught is the dynamic impedance of the circuit. It is independent of the frequency. The impedance is a pure resistance. Lower the resistance of the coil, higher the value of Z naught. Hence the value of impedance at resonance is maximum and the resultant current is minimum. Current is minimum and resonance is maximum. A parallel resonance circuit is also called rejector circuit since the current at the resonance is minimum. In other words, a tank circuit rejects the current at the resonance. So due to minimum current, it is called as a rejector circuit. The current at resonance is I naught equal to E divided by Z naught. Z naught value is nothing but L divided by CR. So that CR divided by L. So E into C into R divided by L. So this is current is called a minimum current. Z naught we already know that L divided by CR. From that it is substituted. So in this video we discuss the parallel resonance for a practical circuit. In one section R and L is connected, in another section capacitor alone connected. In that we analyze the resonant condition. Subscribe the channel for more videos and notifications. Soft copy of this material available in the drive. The link is given in the description box. Thank you for listening.